So there is, I don't know if we should turn off this or just the front line.
Let's see. What?
We need 3 people to turn off lights.
Well.
Oh, okay.
So well, anyway, while they turn it off, I'm Horacio Canales. My talk is Python in metal additive manufacturing, with the case of industrial robotics. I work for the CPT, for the University of Barcelona, but CPT is our research group. We mainly work on a technology that is called thermal spray, but especially in cold spray is what I will show you now. But well, in general, I just want to make a little introduction about the technology that we're talking about. Some applications where Python is being used for research in additive manufacturing here in Barcelona. And then we'll go straight to Python for industrial robotics. And if we still have some time, I would like to make a demo so you can make some experiments at home or just play a little bit if you want. So let's go. Yeah. What is our research about here in Barcelona? We work with powder materials, metals, superalloys, different kind of materials. And well, we do as well additive manufacturing. I would like to put you just a video from General Electric. I think they made a good job just to say what is this technology about and what is used for. So, well, as you see, we spray powder material. To build parts of jet engines that use materials, very special materials that have high resistance. Yes, at high temperatures and very aggressive environments. And as you see, the main idea is that we spray powder, and this powder behaves as a kind of, it kind of melts when it gets on the substrate. Well, it's not like that, but it's the easy way to say it. And well, it's used to build parts of this kind of engines that you use when you fly in the airplanes. And well, there are many, now it's a very active topic in research in the whole Europe, and I think in the world. So I will show you how here in Barcelona we use Python on this research. Well, that is mainly it, is to make this kind of machines and repair them as well. So the problem with this technology is that it's a complicated technology. What I mean with that, if I want to make experiments in order to know if I make I change a parameter like pressure, temperature on this machine, it could take me a lot of experiments in order to get a good result. So here is an example of just to see how big is the possibilities when you're changing parameters. So here are 400,000 different combinations, and just few of them have a good result of 100% deposition efficiency of powder. So when you depending on the process parameters, that is very important to choose the right pressure, temperature, and all speed and many of these parameters. You could get a good material or a bad material. For example, if you didn't choose those ones, you can have here is the some delamination. It deforms when it's not well deposited, or you can have a lot of erosion because it's very high velocity and it just erodes. But on the other side, if you choose a good set of parameters, you can grow very thick material and very fast. So that is very good for the industry. But usually when you fly or go in your car, well, you just get the good material working. But behind that, there's a lot of research. That is what we do in our institute. So what is numerical simulation? It's one of the things that we do. I just want, before going into cold spray, because I want to talk what we do, I just wanted to put a little example of a code of numerical simulation of heat diffusion. So what we do in heat diffusion is that to make an example, you put some temperature in the center for some time, and then you let diffuse that heat. That is done solving this equation that is a Laplacian operator, and then, well, you solve it with code. So if you can see, it's just normal Python using NumPy, CPy, and Matplotlib for this kind of plots. And well, it's a class with some methods, just as you do in many cases, but well, yes, here we can predict how the heat will diffuse on a material. So for every manufacturing process, it has a physical phenomena. So in our special case, that is called spray, the physics that are related to this technology is a rocket nozzle. Just like the rockets that fly to cosmos, we use the same technology. But we use these nozzles, that is this one, we will see it, in order to transfer heat and momentum to particles. So here is just a good example of how the machine works. We put it on a robot. It works also with the parts on the robot, but here we put pressures, gas on high pressure, like between 2 and 8 megapascals. We heat it, then it goes through the nozzle and it accelerates, because a nozzle it transforms the thermal energy to kinetic energy. So once the gas is stabilized, we inject particles, and these particles go out and accelerates until they hit a substrate, as you can see. So we are constantly putting in all these particles in order to form a bulk material here on the surface of the substrate. So once this is the way that the particles go inside, that go very, very fast. They can go up to 1,200 meters per second. Just imagine a kilometer. Imagine that you can pass that kilometer in 1 second. So it's that fast. Thanks to that, we can build materials on top, and well, this is the machine. So in order to make simulation, we need to understand all the physics related to this work. And thus, that is our supplier. In order to simulate the velocity and impact temperature of these particles, well, there's also Python code on the back solving these equations that you can see on the left. So on one side you just solve, this is a drag force you calculate on the momentum transfer, the convection heat transfer, and well, fluid dynamics and all that is behind all this fluid dynamics. So well, the simulation help us to get that information. Why this information is important? It's important because the simulation brings the information that we hardly can get from sensors. Because as it's too fast, I can measure maybe the velocity, but the temperature is, well, at least with the technology, state-of-the-art technology, we can do it. But we can simulate this heat transfer. And well, data analysis brought by Python will help us to see all this data. So for example, I just put out an example of what we do. We have a nozzle, the one that I showed in the last slide, get all the data of simulation data, and using pandas, matplotlib, and seaborn, we can start visualizing how some pressure, temperature, distance, it gives me the velocity and temperature of the particles of different sizes. Because every time that I choose a new powder material, this powder material have a distribution of size distribution, and we need to know how I affect this velocity and temperature. Well, maybe you have seen this in other areas, but well, I have to exemplify how we use seaborn for that, in order to see the quartiles and the media and try to choose what is the effect on material properties at the very end. Also Python help us. This is with pandas. We discretize continuous data in order to see all the possible configurations of the equipment. For example, we have different nozzle designs. We have different powder materials, pressures, temperatures, distances, particle sizes, and on this side we can see how we can select different configurations and how that will affect the particles velocities and particles impact. That also help us in order to get the right process parameters in order to get a good part that you can use. So the ones we have all this data, because you can, well, it depends how much simulation you want to make, but you can get millions of points. And you can go to the microscope, that's what we do, see the powder and then analyze which particles are being bonding, which ones are eroding the material. And for example, this is an example of a logistic regression, so a very simple classification model applied with scikit-learn. So it helps us in the whole particle distribution, which particles are being bonded and which ones are being bounced off of the spraying operation. So here in the red, you see they are predicted not to go inside, and they're ones to go inside, and that helps us to get more knowledge about the process. At the very end, make predictions of how can I get a better deposition efficiency or a better material property. And once again, behind that, it's a lot of Python code. Yes, making the plots and making the classification and all this. Also, scikit-learn was used at the beginning to build up experimental, an iterative experimentation process that we used in order to reduce, for example, porosity of our depositions. This is a stainless steel material that is, it was sprayed with cold spray, but at the beginning we start some experiment like this. At the very end, we get a very dense and good material. And that started with scikit-learn, but then we decided to make a platform online. Now that is deployed on Node.js, but because that it works well with the internet. Yes, I know, but the real motivation was scikit-learn because it's very easy to make a regression or polynomial features. Everything is very, very well documented and documented. Also, we use deep neural networks with TensorFlow and Keras in order to recognize material properties just from a picture of a material. So as you can see, this is we grind materials, and we have training data and all that is behind of data generation in order to predict what will be at the beginning, what will be the material, and then we have some regression tasks that tell us how to make know the hardness, know the tensile strength, and it was a pretty good application. We're still developing more and more, but it won a Microsoft Research Award this year. Yes, of our AI application. Now let's move to industrial robotics a little bit. What we do here in Barcelona related to industrial robotics. When we use the cold spray technology, what we got is this kind of conical shapes or prismas, however you like to call them. They never get straight walls. They are always like this. So that means that we need to play with the robot, with the gun, in such a way that we can fill this side and try to get a straight wall. It's something like what you do for 3D printing, but the difference that 3D printing you can build these straight walls. Here you can't. So robotics and especially Python help a lot in order to get that. Here are some videos of control of these operations. You can see it's rotating and making and filling the sides that are needed in order to build this kind of walls, and all the code behind that is Python. So at the very end, I will try to make a demo. So because maybe you see like this and say, well, how? But we'll see how it helps. How is it to make it? This is it's a great development because with this we can start building parts from zero. It takes it's very fast. 6 minutes is nothing for these materials. You know how much there are other metal additive manufacturing technologies that it takes hours, many hours to build something like this. We can make channels, we can make thin walls. So, well, it's part of the work, and as I told you, Python is behind all these developments. So, Python for industrial robotics. Now to the point. To the best of my knowledge, I will say, because sometimes there are good libraries that are not very well advertised, or well, they are not. It's not easy to find them. I know three solutions. The first one is RoboDK. They have a simulation environment and offline, and they let you make offline programming of industrial robots. It's commercial, but the Python API is open source, and that is very interesting because they also have post-processors that are open source, and well, that makes a big difference. Well, in my case, because you can already use it for other kind of work. The most popular, of course, well, this is ROS, the Robot Operative System. And they have the branch that is called ROS Industrial. It's an open source project, but most of the work, there are a lot of Python, but it's more popular on C++ users. But still a lot of things made with Python. And this one that I never worked with this one, with visual components, but I saw that they also have a Python API for the simulation environments. Well, I cannot say a lot of that because never used this one. Well, this one the most that I use, and this one I use for experimental things like, I don't like it. but well, because in this case, RoboDK is simpler, and you will see how it works. So, the first question when I was about to program a robot was what I need to know. I mean, yes, I know Python, but I need some specific knowledge about how to use it. And my answer, I don't know if everyone will agree, but I think that we need to understand the industrial robot pose. So the pose is a representation of the robot tool position and orientation. What it means that this is the tool of the robot. So we have a tool center point, and this frame that you see, well, these coordinates, they brings a position and an orientation to this point. And we can build different ones in all the simulation domain. So here is something that is important, that it's easy to represent a position. You just need to X, Y, and Z points on the space. But orientation can be represented in many forms, and it depends on the robot manufacturer. So ABB do it one way, Motoman in another way, and they choose, and you get confused at the very end. So it's what I was saying in the abstract of this talk, that when you want to work with many different brands, so usually you have to know a lot of programming language, and not just that, but the ecosystem behind that, and it becomes very tricky. We will see in RoboDK how they did it to make it more easier. So the position is how we say it. We have a point, S, Y, and Z, and you can also always put other points referred to that point. So you can see this one is referred, frame 2 is referred with frame 1. Yes? And a very common way of describing orientation are the Euler Angles. So they just are three numbers that describe the rotation around one axis. So let's say that if you fly in an airplane, if you want to get southeast, something like that, so you may, the plane just do it at the same time, everything. So you rotate one second. Exit, yes. If you want to rotate on the y-axis, you do it this way. If you want to rotate on the z-axis, you do it this way. And, well, x on this way. So at the very end, the combination of them, they will give you this smooth like orientation that you need, and that's the way that you tell to the robot, put on this place with this orientation. So let's make a demo. Let's see if it doesn't fail. And so I will use RoboDK. So you can see how it's going. Let's try to reproduce and make this example better. This is from the RoboDK web page. They give a little example, yes. So first, you may need to download it. It's for free. You can download. They have some limitations when it's not commercial. We have educational license because we are the university. But look here, where is the world? This thing, you can download the many different robot models. Let's choose any of them, or maybe not. Well, the one that we have in the lab is the 24/6, for example. So we download it and put it there. As you see, it has a reference that is the 00 on the simulation domain. And from the bottom, we can choose a tool that will be attached. I will just use a pencil, and it put it on the tool head. Yes. So, I'll put this, and I already have an environment that. I don't know what I have installed there, but what I want to. That doesn't go out. While it's thinking. There is. Well, you see, it's installed this RoboDK, and well, all the things that are behind it. Yeah. So, the first thing that we need now that we have is to make some reference points that are called targets. This is a target, as you can see. It has a position and an orientation. So now it put it on the tip of the tool. We can put it a little bit more down. Well, that's too much. Let me put it 1,000 maybe. Well, yes, that's okay, I think. And rename it to use it. Home. So we can open. Well, I use code for editing programs. It's slower than usual. I think it's a little bit. I was trying what to do for the demo. At the end, I decided well to make the most simple. We'll put it like demo e.py, right? So from RoboDK is just import the library. I will import everything. I know that it's not very efficient, but RoboDK, by the way, it helps you a lot to work with the spatial. I mean, it's an open source library that helps you to work with the spatial operations like Euler Angles to quaternions, rotate on Z, rotate on Y. It's for that, and RoboLink is just the link between Python and RoboDK. And RoboDK interface, yes. So from RoboLink, we will just create an instance of that. RoboLink like this. So well, I'm pretty much just following this example, yes, that you can see it. And I want to make some changes at the very end. So you will see that you can manipulate whatever you want. So the first thing is to have a robot, yes. I'm okay on time. Yeah, because if not, I can put something down.
As you.
No, I like it. I like it.
You are on time.
Yes. So the first thing is that from RoboLink we need to get an element from the RoboDK interface. So here I have to put the item that is my robot, ABB. IRB 2400/16. So it's 16 kilograms that it can hold. I can get as well my the home. Yes, I made a home, so I can just say home is equal the same is equal. Just get the home. Yes. So now that I have the robot and where I want to go, I can just the robot now as an item has some methods that you can use in order to control the robot. So you can say robot move linear. There are different kinds of movements. You can make a linear that will be a straight line between 2 points. You can make a move joint that will find the quickest path between 2 points, and the move C that will make a circle, round movement between these 2 points. So here I will just say move L. Oh, well, it's what I told you. Yeah. And you say where to go, but you need a pose because I get the item, but I don't know the pose. So you will say just home dot pose. That is a method that returns the pose of that specific item. So let me just put the robot a little bit far away from the home and run the script. How it was? Demo, yeah. So as you see, just move to that point, but well, here the orientation is a little bit strange. Sometimes you have to change it. Here maybe, I don't know if it's this way. Well, now it's a little bit more higher. I can change the joints. We had say 6 joints, and here maybe I think the 4th or the 5th is not on the side, on the right. Yeah, something like that. Doesn't matter. Well, it matters because it can make a big problem. So if you look at the at this documentation, at this example, they tell us how to make it go around an hexagon. So let me just reproduce this example, and then we'll make it go into a circle, and then make more things from there. So the code is pretty simple. It's for I in range 7, it says, yeah. You get the angle on depending on radians, if I'm not wrong with that. Good thing that Pi already comes with RoboDK, so well, I don't have to write it. I don't know if it's in Python as well, Pi. No, I don't think so.
P the number.
Yes.
You have temper in math.
In math, yes.
Math.
Yeah, I saw the how they put it, and it comes with the RoboDK. Yeah. No, but I'm just saying. So they ask us to rotate the pose. Here is where we'll create a new pose. We can start from, for example, home. Use the pose. As you see the method, then they make this rotation. They make the rotation of this pose on C, and angle a translation of the point. Well, I put a little bit less, and they rotate it once again because sometimes the joint you have to put it on the right place. So it put it in order. So this is the order that they recommend. So minus angle. And finally, well, they make the robot make a linear movement, move L to the new pose. Yes. So let's see if it works. I don't know. So it makes the as you see, it's an hexagon. I don't know if it. And you can make it a circle. Here you don't have a circle, but you can use the move C, but you can also put like 100 points and say move around those points. And yeah, well, it will be more smooth, as you can see. Also, well, now that you have this code, you can make it a function, for example, just like a def, a circular path, and put a pose ref, let's say, and we can change this home. Yeah, so I'm just And now you can, if you want, have another for cycle and say for in range, let's say, let's make 3 points. You can make like a new pose is equal to the home pose, for example. But this pose I want to translate it just as I did it here, but I want to translate it in y, so it will move on this way. So I'll put it 0. I'll move 50, but times y, and that the first time will be like not moving, and then it will be moved. I hope, if I'm not wrong. Then now I can call the I can call the circular path. Sorry? Sorry. Yeah. You mean that? I missed it out. And let's see. Okay, imbala. Yeah. 2 times. This one is okay? Well, let's see. So it should. This is the first circle, and then the next one should move to the left or to the right. I don't know. Wait, it moved and make a second one, then a third one. So as you can see, it's just about playing with the poses. You can also insert the script here. For example, we can. I like this one because afterward you can use different to make visual interfaces. And now you can make a program to say, I want to move the robot. You can use Ethernet to connect to the robot and make more control. I feel it very powerful. And if you use it inside the RoboDK, that is also Python, you can put it there. And the good thing that it will even show you the path that it will run. Well, I'm just put it. It saves. And well, you run it from here, and you can see how the paths are drawn. And what pretty much is what we say, what we do. And here, well, we make a little bit more acrobatic things, but it's what we do. But you can play, and it's free. I mean, it's okay. If you want to learn about robotics, well, it's not bad. So if you have some questions, please.
Questions? Please wake up.
Yeah. Like you explained, you have a robot and you have a gun attached to it.
Yeah.
How do you control a gun?
Well, just now we don't use Python for that because it's like it uses another kind of interface. I've been thinking about using a Raspberry Pi to a PLC or something like that, but well, that is ongoing research. I think Raspberry Pi will do it. You mean the manufacturing process? That's very interesting. I mean, at the point that we're here, we got it now, it's not very accurate. I mean, we got like 1-2 millimeters, but the idea we're trying to attach 3D scanners. So using machine learning just to get one measure, so do it the other way until you get the accuracy that you want, like a calibration, and that is the main idea, but still research and development. Yeah, we think that we can get a very good accuracy, but now it's like 1.5-2 millimeters. Well, it depends on the material. Well, all sort of. We titanium, aluminum, copper, nickel superalloys, cobalt alloys. We are start working with ceramics. The thing that our research is on 2 sides. We work more on the material at first, all the microstructure and all this, and then we try to make something more interesting. So, yes. Other questions? Yes, it works for only for some materials. For example, materials that aluminum and this, well, they don't have a very wide range. But for example, with nickel superalloys, we can control this hardness.
Can you then say like one part is from the same block, one part is harder than the other?
Yes, we can do that. I mean, actually, the technology at the beginning is used for surface modification, so you can have a material, bulk material of some alloy, and on the top put the same material, but very, very, very hard. So it's for wear resistance and other applications. It's for that. Another question?
Yes, I would like to ask you, you expressed the position of the fan of the cooling the simplest is 3 points along the axis, and there was another way to express the position, it was quaternion with your number.
Well, quaternions, it's like a matrix, and they use it, ABB use it for quaternions, but what I want to say is that, for example, as RoboDK use, in this case, just Euler Angles, but you can, I mean, at the time that I will post-process for a Motoman that use a more strange way of representing orientation, you don't care about that. You always think about the Euler Angles, and that's, I don't know if I answered the question. Yes? Yes, it has, I don't remember, I think it's in the RoboDK library, you can create robots as well. You just specify the joints. I think yes. I mean, I work with industrial robots only, but I saw in the documentation that you can put new joints and, well, build your own, like just like Ross. The bad thing is that ROS you can make asynchronous tasks, and here I still don't know how to do it.
The inverse kinematics, they solve that. If you have more joints than 6, it's not so easy to take the joints from with the prediction. Mathematically, it gets more complicated, and I don't know if they have that.
If they can calculate the kinematics, well, you need. On that side, I'm not pretty sure. If it's have a kinematic solver or this or that. Another question? Yes. Well, thank you.
Okay, we stop 5 minutes, please. People who haven't received, move here. Everybody feel comfortable.